The publication of Perceptrons, An Introduction to Computational Geometry by Marvin, Minsky and Seymour Papert in 1969 stands as a watershed moment in the history of artificial intelligence. This rigorous mathematical analysis of single-layer and multi-layer perceptrons, a specific type of artificial neural network, both illuminated the capabilities of these early machine learning models and, perhaps unintentionally, cast a long shadow over the field of connectionism for a considerable period. To understand the book's impact, one must delve into the intellectual climate that fostered its creation, dissect its core arguments, and trace its subsequent influence on the trajectory of artificial intelligence. The intellectual atmosphere preceding the publication of Perceptrons was one of burgeoning optimism regarding the potential of artificial intelligence. The Dartmouth Workshop of 1956 is often cited as the field's official birth, and the subsequent decade witnessed impressive progress in areas such as symbolic reasoning and natural language processing. Early neural network models, particularly Frank Rosenblatt's perceptron, enjoyed considerable attention and funding. Rosenblatt, a psychologist at Cornell, demonstrated the perceptron's ability to learn to classify simple patterns, fueling expectations that these networks could eventually solve complex cognitive problems. This optimism, while enthusiastic, occasionally outstripped the demonstrated capabilities of the technology, leading to a sense of inevitable progress that Minsky and Papert sought to temper with mathematical rigor. Minsky and Papert's Perceptrons is structured as a mathematical exploration of the computational power and limitations of perceptron networks. The book meticulously analyzes the geometric properties of these networks, demonstrating precisely what kinds of functions they can and cannot compute effectively. A central theme is the perceptron's inability to learn certain classes of functions, most notably the exclusive OR function, often written XOR. In formal terms, XOR is a Boolean function that outputs true if and only if its two inputs differ. Minsky and Papert demonstrate, using geometric arguments based on linear separability, that a single-layer perceptron cannot represent the XOR function. A single-layer perceptron essentially divides the input space with a hyperplane, and the XOR function's true and false outputs cannot be separated by such a hyperplane. The book extends this analysis to other functions and provides a general framework for understanding the representational limitations of perceptrons with limited connectivity and depth. Importantly, the authors did acknowledge that multi-layer perceptrons could compute XOR, but argued that the training algorithms available at the time were inadequate for learning complex functions in such networks. The mathematical treatment involves careful consideration of predicate calculus and its application to pattern recognition, a field then deeply intertwined with earlier AI research. The immediate impact of perceptrons was significant. While the book did not halt neural network research entirely, it substantially curtailed funding and dampened enthusiasm for connectionist approaches. Critics often claim that Minsky and Papert definitively proved that neural networks were incapable of solving complex problems. A more accurate assessment is that they rigorously demonstrated the limitations of a specific class of neural networks, single-layer perceptrons, with the computational tools and training methods available in the 1960s. The book's arguments were persuasive, particularly given the prevailing emphasis on symbolic AI at institutions such as MIT, where both Minsky and Papert held prominent positions. The focus of AI research shifted away from connectionism toward rule-based systems, expert systems, and other symbolic approaches that dominated the field for much of the 1970s and early 1980s. This period is sometimes referred to as the AI winter, a time of reduced funding and diminished expectations. However, the seeds of a connectionist revival were sown even as perceptrons held sway. Researchers continued to explore alternative neural network architectures and learning algorithms. A particularly important development was the backpropagation algorithm, which provided an effective method for training multi-layer perceptrons. While the concept of backpropagation had been around for some time, it gained widespread attention in the 1980s, particularly after its popularization by David Rumelhart, Geoffrey Hinton, and Ronald Williams. Backpropagation addresses the challenge of the vanishing gradient that plagues training deep networks. As the error signal propagates from the output layer back through the network, the magnitude of the gradient can diminish exponentially with each layer, making it difficult to train earlier layers. The backpropagation algorithm, coupled with advances in computing power and the availability of larger datasets, enabled researchers to train multi-layer perceptrons capable of solving complex problems that were previously considered intractable. The resurgence of neural networks in the 1980s and beyond, often referred to as deep learning, demonstrates the complex and often non-linear relationship between theoretical analysis and empirical progress in science. While perceptrons accurately identified the limitations of single-layer perceptrons, It did not foresee the transformative impact of backpropagation and other advances in training algorithms and network architectures. Modern deep learning models, such as convolutional neural networks and recurrent neural networks, are far more sophisticated than the simple perceptrons analyzed by Minsky and Papert. These models have achieved remarkable success in a wide range of applications, including image recognition, natural language processing, and robotics, revitalizing interest in the potential of artificial intelligence. It is important to note that Minsky and Papert's intentions were primarily to provide a rigorous mathematical foundation for understanding the capabilities and limitations of perceptrons, rather than to discourage neural network research altogether. Indeed, both Minsky and Papert continued to contribute to the field of artificial intelligence throughout their careers. Minsky, in particular, remained a strong advocate for the development of artificial intelligence, albeit emphasizing the importance of symbolic reasoning and knowledge representation alongside connectionist approach. The critiques leveled against perceptrons often center on the perceived narrowness of its focus. While the book rigorously analyzed single-layer perceptrons, it arguably gave insufficient attention to the potential of multi-layer networks and alternative learning algorithms. Critics also point out that the book's timing was particularly unfortunate, as it coincided with a period of reduced funding for AI research in general, making it easier to attribute the decline in connectionist research solely to the book's influence. However, these criticisms should be tempered by the recognition that perceptrons played a crucial role in establishing a more rigorous mathematical framework for analyzing neural networks. The book's emphasis on formal analysis and its identification of fundamental limitations served as a valuable corrective to the overly optimistic claims that had often characterized the field. The legacy of perceptrons is multifaceted and complex. It serves as a cautionary tale about the dangers of oversimplification and the importance of rigorous mathematical analysis in scientific research. The book's accurate identification of the limitations of single-layer perceptrons prompted researchers to explore alternative approaches and to develop more powerful learning algorithms. Furthermore, it highlights the importance of carefully delineating the scope and applicability of any scientific theory or model. While perceptrons did not foresee the rise of deep learning, it contributed significantly to the development of a more nuanced understanding of the capabilities and limitations of artificial neural networks. The book's impact is still felt today, as researchers continue to grapple with the challenges of developing robust, general-purpose artificial intelligence systems. The influence of perceptrons extends beyond the technical aspects of neural network research. It also raises important philosophical questions about the nature of intelligence, representation, and computation. The book's emphasis on the limitations of simple models prompts us to consider the complexity of human cognition and the challenges of replicating it artificially. It encouraged a more critical and self-reflective approach to the field of artificial intelligence, urging researchers to ground their claims in solid mathematical and empirical evidence. In conclusion, Perceptrons: An Introduction to Computational Geometry by Marvin Minsky and Seymour Papert is a landmark work that had a profound and lasting impact on the field of artificial intelligence. While the book may have inadvertently contributed to a temporary decline in connectionist research, it ultimately played a crucial role in shaping the development of a more rigorous and nuanced understanding of neural networks. Its legacy lies not only in its accurate identification of the limitations of single-layer perceptrons, but also in its emphasis on the importance of mathematical rigor, critical analysis, and a self-reflective approach to the challenges of creating intelligent machines. The book serves as a reminder that progress in science is often non-linear, and that even seemingly negative results can contribute to the advancement of knowledge. Its enduring historical significance as a key document in the evolution of artificial intelligence remains undeniable.